One of the most famous stories in physics is about Newton and his apple tree. In this story, Newton was sitting under an apple tree when all of a sudden an apple fell on his head and he discovered gravity. But what if the story didn't end there? What if Newton picked the apple up and threw it? In fact, what if he threw it so fast that it orbited the Earth and came back to hit him in the head? In this case, how fast did Newton throw the apple? This can actually be explained by Newton's law of gravitation, which states that the force of gravity between two objects equals a constant g times m, the mass of one object, times little m, the mass of another object, over the radius squared, where the radius is the distance between the centers of the two objects. This is just measuring the pull between the apple and the Earth. In this case, g is a constant which was discovered by a later scientist and is approximately 6.67 times 10 to the negative 11th meters cubed over kilograms seconds squared. From here, we can use Newton's second law, which is force equals mass times acceleration, to describe the force on the apple. Then we can set the force of gravitation equal to the force on the apple, saying that the mass of the apple times its acceleration is equal to g times the mass of the Earth times the mass of the apple over r squared. Here on out, I'm going to use big M as the mass of the Earth and little m as the mass of the apple. This can further be simplified with centripetal force, which states that the acceleration of an object moving in circular motion is equal to its velocity squared over the radius. Plugging this in for A gives us mv squared over r equals g big M little m over r squared. Of course, this equation can be simplified further. By simplifying some of the m's and r's, we get that v squared equals g big M over r, or v is equal to the square root of g m over r. From here, we can plug in our constants. We already looked at g. M is the mass of the Earth, which is approximately 5.97 times 10 to the 24th kilograms. And r, the radius of the Earth, is 6.37 times 10 to the 6th meters. Since the apple is so close to the surface of the Earth, we are going to approximate its value off the ground as the radius to the surface of the Earth as well. From here, once we plug in our constants, we get a value for the velocity at about 7.91 times 10 to the 3rd meters per second. This is ridiculously fast. However, notice that in our final equation, there is no little m. This means it wouldn't matter if Newton threw an apple, a piano, or even an elephant, although forces might have some other problems with this one.